we go. And let's get going, everybody. So last class, we're in chapter 13. We're talking all about equilibria. And we looked at the relationship between equilibrium constant with respect to concentration, so Kc, and equilibrium constant with respect to pressure, Kp. And then we came up with this formula. And I spent a couple of minutes showing you where this formula comes from. And I explained how, you need PV equals nRT to solve for this. And we talked about what delta N is. It's the change in the number of moles of gas. And R is the gas constant, 0.08206. Temperature's got to be in Kelvin. And then we tried one problem. We tried problem number 7. We solved this one last class. And so I want to move forward to question number 8. And I thought we would start here today and try question number 8. So we have a reaction shown here on the top right. Okay. NO2 is in equilibria with NO and a half a mole of oxygen. It says, write expressions for both Kp and Kc for the following reaction. If Kp is equal to 7.6 times 10 to the minus 7 at 25 degrees Celsius, what's the value of Kc? Now, notice that all of these molecules are in the gas phase, right? They're all in the gas phase. And so we can write an expression for Kp that involves each one of these. So since they're gases, they can all exert a pressure. But gases are molecules, right? Or they can be an element, but in this case, they're all molecules. And so they can have a concentration. And so we can write an equilibrium expression for Kp or for Kc. I'm going to start it with Kc because we've done that one a lot. So we'll start with Kc. It's going to be equal to the concentration of NO to the power of 1. So I leave that out times O2 to the power of a half. Remember, it's just the stoichiometric coefficients divided by the concentration of NO2. And there you go, done. Okay, that's the expression for Kc. If I want to write an expression for Kp, the way that I do that is a little different. Okay, you write the pressure, the big letter P of NO, okay, times the pressure of O2 to the power of 1/2 divided by the pressure of NO2, like that. And that's how you would write an expression for Kp. Now we're given Kp, that's given to us, and we want to calculate Kc. So we're going to use our formula that Kp is equal to Kc times RT to the power of delta N. And we're going to rearrange that for Kc. So let's do that. And we're going to write Kc is equal to Kp divided by RT to the power of delta N, like that. Let's go ahead and calculate or write down some of the values that we need here. We know that R is 0.08206 liter atmosphere per mole Kelvin. I need to have my temperature in Kelvin. 25 degrees Celsius plus 273. That gives me 298 Kelvin. What else? My delta N, right? The number of total moles of gas on the product side is 1.5 moles. And the number of total moles of gas on the reactant side is 1. So we have 1.5 subtract 1. So that gives you 0.5. And there you go. And we have our Kp, which is given to us up here. So let's plug some numbers in, and we'll put Kc is equal to 7.6 times 10 to the minus 7 divided by 0.08206 times 298. And all of that will be to the power of 0.5. And so you got to be able to use a calculator in order to do calculations like this. And I simplified it to Kc is equal to 7.6 times 10 to the minus 7 divided by 4.945, so 4.945. I carried some extra sig figs there. My final answer can only have 2 sig figs, and so it's 1.5 times 10 to the minus 7. That is my Kc. I have a quick question for you just to see if you were paying attention during the last class or to see if you understand the formula. Could anybody tell me under what situation Kp and Kc would be equal? When would that happen? Because they certainly aren't equal in this question. Can you repeat that? Sorry, I couldn't hear you.
When n equals 0.
Yeah, when delta n is equal to 0. I see that you're all putting the answer in here. Some people got it. Yeah, it's when delta n is equal to 0. So when delta n is equal to 0, then Kp is going to be equal to Kc, okay? So when delta n is equal to 0. There's no change in the number of moles. So guess, think about it. If delta n is 0 and you're taking RT to the power of 0, it doesn't matter what RT is. Anything to the power of 0 is 1. Okay, so Kp will equal Kc. Anyhow, I just wanted to ask you that because I went through a lot of the problems in the ACS study guide, and what was I going to say? That was one of the questions they asked, was something like that. You know, do you just understand what the hell, how the hell the formula works? Pardon my language. All right, well, let's move on and try another problem. And I introduced to some of you the concept of the ICE table last class, the ICE, the initial change and equilibrium table, the ICE table. And we're going to use an ICE table to solve another problem here. So let's take a look at it. It says you have 0.850 moles of COCl2. That's actually called phosgene. And you're like, what? Phosgene? Shouldn't it have phosphorus in it? No, the phosgene doesn't have phosphorus in it. Phosgene was actually used in chemical warfare in First World War, I guess. Anyhow, I'm not an expert in chemical warfare, but I think it was used then. Anyhow, so phosgene is placed in a 3-liter reaction vessel and allowed to come to equilibrium at 800 Kelvin. Here's the reaction that expresses the equilibrium, and it says after equilibrium, and this is kind of the key here, you know, being able to interpret problems. It says 85.9%, where's my 85.9% of the phosgene, COCl2, remains. Figure out what Kc and Kp are. All right, let's see if we can do this. I'm going to start by calculating the initial concentration, right? I'm going to start by calculating my Kc. So what's the concentration of my phosgene, right? The concentration of COCl2, and I'll call it I like that, and that just means initial. Well, let's see, I have 0.850 moles, and the size of my container is 3.00 liters, so just plug the numbers in a calculator, and you get 0.283 moles per liter, or molar. Okay, that's what we're starting out with, right? Think about it. All we're starting out with is just this. Some phosgene in a container, and then we let stuff happen, and then we evaluate it, right? So let's start to evaluate it. I'm going to rewrite the balanced equation. So phosgene is in equilibrium with carbon monoxide and chlorine gas. I have my initial concentration of phosgene as being 0.283 moles per liter. I don't have any of this, and I don't have any of that. Nothing. Okay. Now, what it's telling me is that I'm going to have a change, and that at equilibrium, it says that 85.9% of this 0.283 is going to get consumed. So if you grab your calculator and you take, and I've got mine right here, okay, you can see it, 0.28. You know it's me doing it because I always press the wrong buttons. 0.283 times 0.859, you end up with 0.243. Okay, so at the end, once it's done, you've got 0.243 molar, right? Because you've consumed, so we'll say 85.9% remains. Okay, you've consumed some of it. You consumed about what? What would it be? 14.1% was consumed. Okay, there you go. Now let's fill out the rest of the table. Well, since the stoichiometric coefficient of everything is 1, okay, and since we consumed some of the phosgene, we can say, well, you lost X, right? You lost some of the phosgene. And again, since the stoichiometric coefficients of the carbon monoxide and the chlorine are the exact same, we're going to put plus X here and plus X here. Now the question is, what the hell is X? Well, X is going to be equal to 0.283 molar subtract 0.243 molar, right? That's how much was lost. Okay, so we take that and we get that X is equal to 0.040 molar. Okay, and if we gained X over here and gained X over here, right? If you take 0 plus X and 0 plus X, you end up with X. So we have X over here, and we know what X is. We know that at equilibrium, I'll just rewrite it. We have 0.243 molar of this. We have 0.040 molar of this and 0.040 molar of that. There we go. Now we can write an expression for our Kc, can't we? We can say that Kc is equal to the concentration of CO, carbon monoxide, times the concentration of chlorine divided by CoCl2, and we get the Kc is equal to 0.040 squared divided by 0.243. You punch that in your calculator. It's got no units, right? We don't report a unit for our Kc or our Kp, and we get 6. I put an extra sig fig in my answer. Mr. Dion, you are slipping. Anyhow, I put 6.58. That's one too many sig figs. Let me think here. Yeah, it's too many sig figs, but I'll leave it in anyway. Just in case I did it in my solutions. Anyhow, technically it should be 6.6, but whatever. I'm never going to ask you a question where the equilibrium constant is 6.58, 6.59, you know? I'm never going to try to trick you like that. Unless the question is specifically about, you know, sig figs or something. Anyhow, so let's take the rest of the space here and see if we can solve for our Kp. We know our formula Kp is equal to Kc times RT to the power of delta N. Let's plug in some numbers. We'll say that our Kp is equal to 6.58 times 10 to the minus 3, all multiplied by 0.08206 times our temperature. What's the temperature? Where is it? Is it 800 Kelvin? Yeah, there we go. Times 800. I'm leaving the units out because Kp is unitless. Times 800. Hey, I'll ask you guys, can anybody tell me what delta N is? It's not a trick. Yeah, the delta N would be 1, right? Because you have 2 moles of gas on this side and only 1 mole of gas on this side. So delta N is equal to 2 minus 1, which equals 1. So we have all that to the power of 1. There you go. And we have Kp is equal to 4.32 times 10 to the negative 1. So Kp is equal to 0.432. Anyhow, there we go. So you've got to be able to use an ice table. All right, you've got to be able to, you know, use an ice table in general chemistry too. And I promise you, we're going to do some more practice on ice tables. In fact, I don't think we'll have time to do every single problem, you know, under the sun, but let's take a look. I want to skip ahead and we'll come back to question number 10 if we have time at the end of the chapter. So we'll do that. We'll call this one a maybe. Again, the solution to this one is posted on Canvas. You've got it. I'm not leaving you with no solution. Okay, you got it. I wanted to do this one here because this one involves something a little bit special. If you're like, oh boy, what could it involve? Has anybody tried this one? Maybe I shouldn't ask questions that, you know, I don't want to hear the answer to if it's no. Has anybody tried this one? No? Okay. All right. I recommend giving them the old college try. Not yet. Okay. Well, let's try it now and see if we can figure this one out. Again, it's going to use a nice table. It's really similar to the last thing, you know. But we're kind of turning the heat up here a little bit, you know, just in terms of intensity. So let's take a look at the problem. It says it's 600 Kelvin. Kc is equal to 0.542 for this reaction. So, hey, we're even given the Kc. But it says if 0.200 moles of carbon dioxide and 0.100 moles are put in a 2-liter flask, what is the equilibrium concentration of each species? Okay, so you know the Kc, but they're telling you that you start it with this much, and then you let the reaction come to equilibrium, and then it says what's the concentration of everything. So let's write out an ice table. I think that's the best place to start. So we'll write down CO2 plus H2 is in equilibrium with carbon monoxide plus H2O. There we go. So we have initial. What's our initial concentration of the two things we have? CO2 and H2. So we have 0.200 moles in how much? 2.00 liters. And here we have 0.100 moles in 2.00 liters. And we have none of this and none of this. So that means that initially we have 0.100 molar of this and 0.0500. There are 3 6 figs in that, right? molar of this, and we still have none of this. Okay, so let's write down our change. This one is not that bad because the stoichiometric coefficient of everything in here is 1. Okay, so the x's are going to be minus 1x and plus 1x. Well, think about it. In terms of the equilibria, if I have all of this and I have none of this, and I have a Kc of 0.542, that means I'm going to have to lose, let me get back to my black pen here, you're going to have to lose x over here, and you're going to have to gain x over here, right? That's going to be our change. So at equilibrium, we have 0.100, and I'm going to leave the units of molarity out because you don't need them to calculate a Kc. Anyhow, 0.100 minus x. Here we have 0.0500 minus x. Here we have x, and here we have x. Now, we know that our Kc expression, not Kp, Mr. Dion, Kc is equal to concentration of CO times concentration of H2O divided by concentration of CO2 multiplied by concentration of H2. Let's plug in our numbers. On the top, we have x and x, right, for here and here. What's x times x? We have x squared on the top divided by 0.100 minus x times 0.0500 minus x, like that. And all of that is equal to my Kc, which is equal to 0.542. What does this look like to everybody? Do you guys remember a polynomial? Right, we have x squared and x. So this is a polynomial function, and you have to simplify this polynomial function. So first, what you're going to do is you're going to multiply out the denominator. I'm going to do this one time in class, okay? This is, I don't mean to sound like a meanie or a jerk or something like that, but I learned this in the 10th grade in 1993 with Mr. Vaughn, V-A-U-G-H-N, Mr. Vaughn, okay? Anyhow, so Mr. Vaughn taught me that you multiply the denominator out first. So we get that our Kc is equal to x squared divided by 0.00500, subtract 0.150x plus x2. And again, that's equal to 0.542. You simplify that further, and I got the x squared is equal to 0.54, sorry, where am I? 0.5, no, that's not right. X squared is equal to 0.542 x minus, no, 0. Oh, shutter. Where am I? I made a mistake in my notes here. So 0.542. All right. Sorry, I'm just thinking here. Oh, no, it's right. It's right. Minus. Anyhow, I'll simplify it even further because I didn't make a mistake over here. Anyhow, you simplify it further. And finally, I ended up with this polynomial. So you get 0.458 x squared plus 0.0813x minus 0.00271 is equal to 0. So there's your polynomial function. Can anybody tell me how to solve for x? What formula would I use to solve for x? And it's not a trick question.
Quadratic equation.
Yeah, use the quadratic equation, right? Which is x is equal to negative b plus or minus b squared minus 4ac over 2a. Mr. Vaughn can't be that pissed. He gave me a scholarship, so all right. The Samuel Margolian math scholarship. So okay, anyhow, so you use the quadratic equation. That's one way of doing it, is doing it the old-fashioned way. If you have a calculator like the TI, if you have the TI 36X Pro, you can use the polynomial function in that to solve for x. So I'm not going to solve I'm not going to go over solving a quadratic equation. And when you do solve for x, you get that x is equal to 0.0287 molar, like that. So there's x. So now we know that the concentration of carbon monoxide and the concentration of water are both equal to 0.0287 molar. The concentration of CO2 is going to be 0.1 subtract 0.0287. So the concentration of CO2 is equal to 0.0713 molar, and the concentration of hydrogen is going to be 0.05 subtract this number, and you end up with 0.0213 molar. Okay, so you've got to know how to solve a quadratic. Again, on my calculator, so I'll show you quickly. And I don't know if you'll be able to see it or not, but this is the calculator that I use. It's cost $20, I think, so it's not a fancy calculator. But if you press second function, I can't see here, second function poly, it'll come up with something like this, and you can either go with different polynomials. So you have the first one, which is ax squared plus bx plus c is equal to 0. You click enter. You put in your a, which in this case is 0.458, enter. Then it asks for your b, which is 0.081813, enter. And then your c, which in this case is negative 0.00271. Then you go down to solve. You click enter, and you can see that I must have entered a number wrong, but anyhow, it's very close to the correct answer. Right here, it gives you x, and then you can scroll down, and then you have a negative value of x, and you ignore that. Yeah, it's not that fancy. Literally, I swear on the Bible, this calculator costs like $20. Okay, now in Canada, it's like $400 or $500, but down here in the States, it costs next to nothing. So you got to know how to solve a quadratic, and the quadratic equation will come up several times in the course. So don't think, oh, I'll never have to do that. Yeah, it'll come up again and again. All right. If you look in the slides, let me go back to presenting here. Just give me a second. There we go. Can you guys see my screen again?
Yeah, we can.
Okay, thanks. Again, it's the TI-36X Pro. I'm telling you, you can Google it right now. Maybe somebody can tell us how much it costs, but I think it's like $20. Okay, $20. It doesn't cost a whole lot. It's a pretty cheap calculator, and it's got that polynomial function, which is pretty handy when you're on an exam. You don't want to work out the quadratic formula. I mean, I have some students who are just so fast at math, that make my head spin. And those people are just like, Mr. Dion, I can just use a calculator, just the most basic calculator in the world and do everything. No problem. That's great. If you want to use the quadratic equation, by all means, go ahead. I noticed yesterday I was going through these problems. In number 12, there's some kind of problem with my solution. So we're going to skip this question for now. I noticed that there is a mistake. There's a mistake somewhere in the numbers in here. I'll have to figure out what it is. But let's switch gears. We spent enough time doing some problem solving, and you're going to have to listen to me talk a little bit more. And we're going to discuss heterogeneous equilibrium. And this takes us right back to last class, right? Last class, I don't remember who it was, but somebody in the chat asked a really good question. Said, hey, Mr. Dion, what happens if you've got a solid or a liquid? And I think I quickly said, well, we're going to discuss it later, but you would ignore those. And we call that kind of situation where we have more than one phase, we call those heterogeneous equilibrium. Okay, here's an example. Let's say you had calcium carbonate, which is a solid in equilibrium with calcium oxide and carbon dioxide. Well, we can ignore the concentration of the calcium carbonate and the calcium oxide, the two solids, because it's a solid. A solid doesn't have a concentration. Its concentration remains constant, doesn't remain solid. It also says here, if you have a pure liquid, and I think my student asked that too. So if you see anything with solid or liquid next to it like that, you can just leave that out of the equilibrium expression. So if you had this reaction right here and you wanted to write out the Kc, the equilibrium constant with respect to concentration, that's it. You're like, I leave all this out? Absolutely. It's not in there, right? Because they don't have concentrations. A solid doesn't have a concentration. And when we see pure liquids, they don't have concentrations either. So we'll leave those out too. the concentration of the calcium oxide and the calcium carbonate, so to speak, are contained in the equilibrium constant. Anyhow, there we go. Now, keep in mind that anything that is a gas, so anything that's a G, and anything that's in solution, all right, anything that's in aqueous solution, always has to be included, right? Because their concentrations can change, right? The number of particles per unit volume. All right, well, let's talk about manipulating the equilibrium expression formula. You know, if I want to just tell you the God's honest truth, this slide is kind of just like some rules, is really all it is that you have to have memorized. You have to commit these to memory. I will not give you these on an exam. You just have to know how to manipulate K if an equation is manipulated. If you're saying like, what do you mean, Mr. Dion? Well, let's say you have a reaction, just a plain old reaction here. And if I was to ask anybody who's hearing the sound of my voice right now, I'd say, hey, you guys, can you write me a KC for this reaction? I guarantee you that you'd all nail it, right? You just write something like that, like, okay, I got it, man. I've seen it a million times. Well, what happens is, what if you wrote that reaction in reverse? What would the KC look like then? And then I'm sure you'd say, okay, let me just call it KC prime, and it's going to be equal to this, right? Concentration of the products to the power of their stoichiometric coefficients divided by the concentration of the reactants to the power of their stoichiometric coefficients. But if you want to answer the question, what the hell is KC prime? It's just the inverse of the original KC. Okay, so the bottom line is when you reverse a reaction, the KC prime, the new KC, is just going to be the reciprocal. Okay, 1 over the old KC. All right, so that's rule number 1, I guess. The next one is, what if you multiply it by a factor of n? Well, if you multiply all the stoichiometric coefficients by a factor of n, say you multiplied them by 2, for example, well, then your equilibrium expression is going to be, you take that Kc, and it's going to be now Kc to the power of n, and that's going to be your new Kc. So if you multiplied it by 2, you would square your old Kc, right? If you multiplied it by 3, you would cube it, so on and so forth. And then if you're wondering, well, how would I calculate it? You know, if I had concentrations, you would multiply all of their stoichiometric coefficients by the factor, and then you would use that as your power. Okay, so kind of like 2 rules that are on here. Maybe you could call this rule number 1, you could call this rule number 2. There's another one that deals with coupled equilibria, and I took this directly from our textbook. You probably noticed that sometimes I take things straight out of the text, sometimes I don't. I kind of do it my own way. Anyhow, it says here, if you have 2 or more equilibrium equations that you're going to add together to give an overall equation, then the new Kc for your equation, that's the result of the addition, is going to be the product of the 2 Kc's. Okay, so let's say you wanted to add these 2 reactions together, right? If you add those 2 reactions, A is in equilibrium with B, and B is in equilibrium with C. If you put those together, you end up with this. Okay, so how would I come up with the Kc? Well, I just told you that you would multiply these. So let me show you. You'd say Kc, we'll call it Kc prime, is going to be equal to the concentration of B over the concentration of A multiplied by concentration of C over concentration of B. Well, what do you notice? You notice that the 2 B's are going to cancel, and you're going to end up with Kc prime is going to be equal concentration of C over concentration of A, which is exactly what's shown right here. Okay, so you just multiply the 2 K's whenever you add 2 reactions together. So we could maybe call that rule 3, I guess. Rule 3. So with those 3 rules in mind, and don't worry, there's no problem if you go back in your notes and you want to refer to the rules or whatever. I have no qualms with that whatsoever. I don't expect my students to have learned everything I talk about in class in the first 10 seconds. I'm not that crazy, okay, partially crazy, but we're going to use those rules today. I guess you call them rule 1, 2, and maybe we'll call this one rule 3. Anyhow, let's get some more practice in. Let's start with something that's a little, I'd say, an order of magnitude simpler. It's asking us to write an equilibrium constant expression for the following. We'll write KC's for both of these. Let's start with A. And again, I'm sure that most of you could probably do this even faster than me by now, but let's just walk our way through it. So if we want to write a KC for A, it's going to be equal to what? Could anybody tell me in A if there's going to be anything that I'm going to leave out?
The aqueous solutions?
No.
The solids.
Right. We're going to leave out
Solids.
solids, okay? Yeah. So we're going to exclude, not excluded, we're going to exclude anything that's a solid or a liquid, okay? We're going to include anything that's gas or aqueous, okay? Right, so we're gonna, you don't cross these off, but I'm just telling you, we're gonna leave out the silver and the zinc, right? We're gonna leave those out and we're gonna include the ions because they're solvated, they're aqueous. So that means our Kc is gonna be equal to the concentration of zinc 2 divided by silver plus, and that's it, my friends. That's the answer. And if you're like, Mr. Dion, please make the entire exam that. Like, well, I might have a question about it, but it won't be the whole exam. If we look at
Wouldn't
B,
Ag have an exponent of 2 because of the 2 next to it?
absolutely. Yeah. I was testing you, and you got it right. There we go. All right. So for B, same thing. We're going to leave out the iron, and we're going to leave out the iron 2 oxide. So we'll leave those out, and we get that Kc is equal to the concentration of CO2 divided by the concentration of carbon monoxide, and that's it. You know, and if you wanted to write a Kp, for it, you'd say the pressure of CO2 divided by the pressure of carbon monoxide. Okay, since they're gases, either one works. Okay, there we go. So remember, these are what we call heterogeneous equilibria. More than one phase, right? Solids and aqueous, and then you have solids and gas. Okay, well, there's 13. Let's move on to 14. Okay, let's see here. Some of these problems that are longer, I like to solve them ahead of time, you know. Let's see here. Question 14. Says 4.80 moles of solid graphite and 4.80 moles of carbon dioxide are put in a 2-liter flask at 527 degrees Celsius. Who wouldn't want to do that, right? At equilibrium, it is found that 71.2% of the solid graphite has reacted. So remember the last question, it said like 85.9% remains. Here it's saying 71.2 has reacted. So, you know, 100 minus 71.2, that's going to be what remains. Anyhow, we have the equation, asks us to calculate Kc and Kp. I don't know why I put the answers in there, but whatever. It's the land of the free. So let's see here. What do we have? 2-liter flask. Sorry, I'm just thinking out loud here. I'm going to give you guys a second to think about this while I think about it. All right. I had lecture this morning. I don't think I'm drinking enough water. All right. Who's enjoying Gen Chem 2? Just me? All right, I guess it's just me. Okay. Anyhow, let's it's not bad. It's great. It's a lot of fun. I find this class to be, I would say this in front of even an organic chemistry class, which is, you know, I'm part of the organic chemistry faculty, really. I have to say this is the most rewarding of all the classes to teach, general chemistry too. It's the most rewarding. It gives you the best feeling. Anyhow, you always feel like you accomplished something when you solve a problem in this class. Anyhow, where the hell were we? Let's see. Let's start out by making a nice table. Let's rewrite the equation. We have carbon solid plus carbon dioxide gives you 2 moles of carbon monoxide. Well, initially, we have 4.80 moles of this, and we have 4.80 moles of this, and we have none of this. Okay, now we have a change, then we have an equilibrium, and it tells us that at equilibrium, what is it? 71.2% of it is reacted. So if I take 100 and I subtract 71.2, right? If you take 100, subtract 71.2, you get 28.8%. So that's how much should remain. So we'll put here 28.8% remains, like that. So if you take 4.8 times 0.288, you end up with 1.38. Does that look right? There we go. You end up with 1.38 moles left over. Okay. So there we have it. So if you look at the stoichiometric coefficients here, this is kind of new. We have 1 here, and then we have a 2 here. So that means that since we're only starting out with the reactants, right, the reaction is going to have to shift to this direction. We know that we lost x over here, and we're going to lose x over here, and we're going to gain 2x over here because the stoichiometric coefficient is 2. Now, what the heck is x? X is going to be equal to 4.80 moles, subtract 1.38 moles. Let's see here. 4.8 subtract 1.38 is 3.42 moles. So we have 1.38 moles here, and we have 2 times 3.42 moles. That's it would be equal to what? 6.84 moles. So let's calculate the concentration of everything at equilibrium. We don't have to worry about the concentration of the solid, so I'll just skip that because it's a solid. But this one, we have 1.38 moles divided by 2.00 liters, and we have 6.84 divided by 2.00. So if I take 1.38 divided by 2, I get 0.691 molar of CO2, and I end up with 3.42. I didn't even have to do that one. Molar of my carbon monoxide. So this is at equilibrium. There's no concentration for a solid, but there you go. Now we've got it. So if we want to calculate our Kc, okay, it's going to be equal to CO2. No, CO, carbon monoxide to the power of 2, divided by CO2. Okay, so that gives us 3.42 squared divided by 0.691. 3.42 squared divided by 0.691 gives you 16.9. So 16.9 is equal to your Kc. Like that. And then for our Kp, maybe I'll solve it over here. So we derived, we have the formula for Kp, which is Kp is equal to Kc times RT to the delta N. Can anybody tell me what delta N is in this case?
Zero?
No, it's not 0.
-1.
No, it's not -1.
It's just 1.
Just 1, right? Because you have 2 moles of gas over here and 1 mole of gas over here. So 2 minus 1 equals 1. So 0.008206 times our temperature, 527 degrees Celsius. You add 273 to that. That's an easy one to do in your head. You get 800 Kelvin. And the whole thing is to the power of 1. So you just multiply that all out in your calculator. You take 0.08206 times 800 times 16.9. Boom. And you get 1109 point spinach. There should only be 3 sig figs. So Kp, we'll say, is 1.10 times 10 to the third power, like that, which is the same thing as 1,110. Either way. Now, something that you might notice here is I did I started with the number of moles here, right? If you're wondering, like, why did you use moles? Because in the other problem that you solved, Mr. Dion, you started it with concentration. You started it with the number of moles per liter. The reason I can't do that is because what they told me is that I'm starting it with 4.8 moles of solid graphite, right? So since it's a solid, I'm not going to express it in concentration, right? When was the last time you took a solid chunk of something in the lab and said, hey, look at this piece of magnesium. Its concentration is, there's no such thing. You don't grab a piece of lead and say, hey, what's the concentration of that gold bar? This doesn't exist, okay? And since they told me that I had 71.2% of the solid graphite remaining, that's why I left it in moles, okay? And I said, well, you're going to lose X and you're going to be left over with this many moles. And that's how I solved the problem, right? Because it's a solid. So it's a little bit of a nuance here. Give me a thumbs up if you follow me on the problem. You're like, I think I could do this one.
I have a question. Why did we not just disregard the graphite to begin with?
Because even though the graphite, so when you disregard the graphite, so I see what you're saying. You're saying, I thought the graphite wasn't important. The graphite is important in the reaction, right? The graphite is totally important in the reaction. You need it, right? It's part of the balanced equation, right? This is graphite. Carbon in the solid phase can be either diamond or graphite. But anyhow, there's our graphite. The graphite is important in the reaction. It's not important in the equilibrium constant. That's where you disregard it, okay? Think back to general chemistry. Think back to general chemistry. Remember when you did a whole chapter on stoichiometry, limiting reactants, right? All that kind of stuff. How many moles of this are produced? You worked with solids all the time. You worked with pure liquids all the time in those kind of problems. It's not that the graphite is inconsequential in the reaction. It's totally of consequence in the reaction. It's just inconsequential in the equilibrium constant. Does that help?
Yes, thank you.
Okay, good, good. You know, some things like that are maybe not evident. That's a really good question. You know, really good question. Thought-provoking question. Well, I just want to look ahead at my notes while I'm doing that. You can look at this problem quickly. Maybe we'll come back to 15 because I want to talk about Le Chatelier before the end of the class today. So I'm going to skip question 15 for now. We'll write a later by that. And you could give that one a try too. You don't have to solve a quadratic in number 15. So maybe you could try that. Or hold on, do you have to solve a quadratic? No, you don't. So let's skip this one. I want to get ahead a little bit here. I want to plow through a little bit because I want to move on to my goal for today was to get into this section, section 13.3. And I know that you talked about Le Chatelier's principle in general chemistry, but I really wanted to talk about it on Friday. I didn't want to wait the weekend and not having discussed it. So let's try a couple of problems here, really quick ones. These are just applying those rules that I told you about where you manipulate K. It says use the information provided in the previous problems where the equilibrium constant is 0.245. Calculate the value of Kc for the decomposition of 1 mole of ammonia gas into its elements at 500 degrees Celsius. So I don't know if you remembered this, but we looked at this last class like 3 times or something. It came up. It was the formation of 1 mole of ammonia from its elements. So if you form 1 mole of ammonia gas from its elements, you have 3/2 H2 gas plus 1/2 N2 gas. And we said that the Kc for this reaction was 0.245. Okay, so again, this is the formation of 1 mole of ammonia. Anyhow, so if we reverse it, right, this is formation. Okay, so if we do decomposition, we're just going to reverse that reaction. So it would look like we have ammonia decomposing into 1/2 a mole of N2 gas plus 3/2 moles of H2 gas. So what's our new Kc going to be? It's going to equal what? It's going to be equal to 1 over the original Kc. So Kc prime for the decomp is going to be equal to 1 divided by 0.245. That equals 4.08. 4.08 is equal to our new Kc. So again, that was what? The first rule that we looked at. Okay, let's move on from there. Let's try one more. It says Same thing. Maybe I'll just copy and paste. It says calculate the value of K for the decomposition of 2 moles of ammonia gas into its elements. So let me copy all of this. Oops, what's that? Come on, there we go. I'm gonna copy this, so copy, and then we'll move over here. I'll try to paste it. Come on, there we go. So we know that the Kc for the decomposition of 1 mole of ammonia is 4.08. So what would the reaction be? The decomposition of 2 moles would be 2 NH3 gas decomposes to give you N2 into gas plus 3 moles of H2 gas. Okay, and we said that the new Kc, so our Kc for this reaction, we'll call it Kc double prime. I don't know, you can call it whatever you want. It's going to be equal to Kc prime to the power of 2, right? When you multiply by a factor, you take the equilibrium constant and you put it to the power of that factor. And so it's going to be equal to 4.08 squared. And so we get that Kc double prime is going to be equal to 16.6. Okay, so just a little practice with those rules. And here's where I really wanted to get to today with you guys is section 13.3, which is Le Chatelier's principle. Le Chatelier. All right, so let's talk about Le Chatelier's principle. Here's a picture of Le Chatelier. You can set your watch to that haircut, right? Anyhow, it says here, Le Chatelier's principle. First of all, does anybody remember Le Chatelier's principle from Gen Chem 1? You would have talked about it quite a bit in there. I know I introduced it to my students. Has anybody heard of this before? No? Okay. If not, we can get into it. All right. So Le Chatelier's principle is really great because it's going to enable you to make some predictions about what's going to happen, you know, if we add heat or if we remove heat from a reaction, if we add a reactant, if we take a reactant away. And I'm going to show you how to make these predictions, okay? So here's Le Chatelier's principle. It says that if a system that's at equilibrium is exposed to some kind of stress, okay, it's going to shift the equilibrium in whatever direction it's got to in order to reduce that stress, okay? This is maybe more succinctly summarized, but that's basically what I said. So you've got a system at equilibrium, you disturb the equilibrium. I'm getting really, anyhow, you disturb the equilibrium, and then the equilibrium is going to do whatever it's got to do to resist that disturbance and get back to equilibrium. So let's think about reactions at equilibrium, and let's talk about what kind of effect would we have on an equilibrium if we were to change the concentration of a reactant or a product. Well, it says here that the concentration of a component, whether it's reactant or product, when you have a system at equilibrium, the reaction is going to proceed in a direction that minimizes that change until a new equilibrium is reached. Now, I don't have anything written down here, an example of this, but let's just think about it for a second. If you had reactants produce products and you increase, maybe I'll do it like this. If you have reactants, okay, and this is the simplest possible example I can do, in equilibrium with products, if you increase the concentration of the products, and you know that Kc is equal to the concentration of products over the concentration of reactants, right? If you jacked this up, what would that do? That would jack this up, and that would make a larger Kc, right? Which would be a Qc, but your Qc would be greater than Kc. And so what would happen to the equilibrium? It would shift to the left. It would have to go back this way to make more reactants to balance it out so you can reestablish equilibrium. Give me a thumbs up if just what I said makes some sense to you. If you're like, I'm not 100%, but even if you're just like 60% of the way with me, like, I think I understand what you're saying. Okay, cool, good. Well, at the bottom, it kind of alludes to what I said, the Q and the K. It says when the concentration of a chemical species in some kind of system at equilibrium is changed, the system is no longer going to satisfy Q is equal to K. Another way of saying that is it's just not going to be at K, right? It's going to be at some other value, which we call a Q, a reaction quotient. And remember, It's just like my buddy who tapped me on the shoulder in industry and said, look, buddy, molecules and atoms are going to do what they're supposed to do. So the reaction is going to do what it's got to do to get back to K, to get back to equilibrium. Okay? So let's go over all these scenarios. So here's that simple example that I gave you. You got a reaction. Reactants is in equilibrium with products. Doesn't get any simpler than that. Here's your K. Concentration of product divided by concentration of reactants. Okay? What's going to happen if the concentration of a reactant is increased? Okay? It's asking us, which direction is the equilibrium going to shift to? Is it going to shift to the left or to the right? So in A, son of a gun, what's going on? There we go. If we're increasing the concentration of a reactant, right, if we're jacking this up, right, then we're going to have a Q that's lower than K. If you're like, well, how do you know that, Mr. Dion? Well, think about it. Let's imagine your K was equal to 1 over 1, okay, which is going to be equal to 1. That's an equilibrium. Well, if you jack up the concentration of reactants, then your Q would be something like 1 over a higher number than 1. Let's imagine it doubles, okay, which would give you 0.5. That means that your Q is less than your K, right? And then the equilibrium is going to have to shift towards the right in order to reestablish equilibrium. Okay, so shift to here. We'll put shifts to right, like that. So I want you to do, and I don't do this a lot in this class, but I want you to take a few minutes and I want you to try B, C, and D. And just, it's not meant to be a mind-boggling exercise. I just want you to see if you can figure it out on your own, and then we're going to come back and discuss it. So I'll give you like a minute to take a look at it. Okay, so let's take a look at B. It says if the concentration of a reactant is decreased. So if this drops, right? And I'll go over the scenario one more time with you. So imagine you have your K, which is equal to 1. So in this case, if the concentration of the reactant drops, it's lower, then you would have a higher concentration of products than reactants. So then let's say your Q is equal to 2, and these are just numbers that I'm throwing in there. That would mean that your Q is greater than your K. And so the reaction is going to shift to the left in order to reestablish equilibrium. Who got that one? Did anybody get that? All right, good. Where am I? Okay, maybe nobody got it. Okay, good. Thanks, Violet. I'll take that to the bank. Okay, let's try C and D quickly. Maybe you guys find this easier than I think. Anyhow, it says if a concentration of a product was increased. All right, if I jack the concentration of this up, the reaction is going to have to shift to the left, back towards the reactants to reestablish K. So we'll put here to the left. Okay, so we'll erase that. And then if the concentration of a product, if that gets dropped, then it's going to have to shift to the right to reestablish equilibrium to increase the concentration of the products. Anyhow, I mean, you can analyze it by looking at Q. You can just analyze it in your head. But more often than not, you're going to have to kind of be able to solve these in your brain and just say, okay, well, here's the effect, that's going to be a result of this change in concentration. Now, something that's important to note is that if you add or remove a pure liquid or a pure solid, it's not going to do diddly squat to the equilibrium. Why? Because they don't have a concentration. Okay, so they're not going to affect the equilibrium. Now, I would say that there's an exception to this rule, kind of, and that would be if you were to remove all, let's say you had a solid in an expression, in some kind of reaction. If you removed all of the solid, or if you removed all the liquid, I would say there's a slight exception here, and we'll look at an example that involves that. Anyhow, this is because pure liquids and pure solids do not appear in the equilibrium expression. All right, let's move on from there. Le Chatelier's principle. Nothing mind-boggling in question number 18. It just says we have some kind of equilibrium. We have A, which is a solid, plus B, which is a gas. You see why phases are so important. How will this equilibrium respond if all of the A is removed? And this is what I was getting at, right? If you remove all of it, so all of A is removed. Now I know that only these two members are part of the equilibrium expression, but as I was mentioning to you earlier, okay, the A is part of the reaction. And so if you removed every last molecule of A, then you don't even have this reaction anymore, do you? You've got something else. You've only got B and C. So in order to reestablish the equilibrium, the reaction will have to shift to the left. So reaction will shift to left, but it's not going to affect the equilibrium constant, right? So that's what one of my students wrote, and you're absolutely right, because the K, right, the Kc would just be the concentration of C over the concentration of B. But we're talking about Le Chatelier's principle, right? Anyhow, let's try another one here. This is question 19. It says, how can you determine in which direction a reaction is going to proceed if the concentration of both the reactants and products are changed in a system initially at equilibrium? Let's just make this really simple. I would do this. I would calculate Q, the reaction quotient, and compare with K. And we've been doing that since the last lecture, right? We looked at all kind of examples where we compared a Q and a K, didn't we? Did that many times in the class already. Well, let's take a look at another practice problem. We got a few minutes left. We got 15 minutes left. Let's give it. Let's see here. It's that same old reaction that keeps showing up, the phosgene in equilibrium with the carbon monoxide and the chlorine. Okay, I remember this problem. I took it from another textbook. I don't know if any of you have ever heard of the Chang textbook. So Chang is a famous author. He's a Chang Goldsby. It's a famous first-year chemistry book, but I took this question from that book. Anyhow, it says you have the following reversible reaction. Beautiful. At equilibrium, hey, it tells you at equilibrium the concentration of everything, okay? An additional 0.1 molar of phosgene, COCl2, is injected into the equilibrium mixture. Calculate the concentrations of each species when the equilibrium is reestablished. Let's go over this kind of slowly here. The first thing we're going to do is calculate Kc, right? Because we know that Kc is equal to the concentration of carbon monoxide times the concentration of chlorine divided by the concentration of phosgene. And we have all those concentrations at equilibrium, right? It tells you right here, it's at equilibrium. So let's plug those numbers in. We've got 0.243. I'm going to square that because both of these are 0.243, right? So I just put to the power of 2 divided by 0.0400. And you punch all that in and you get your Kc is equal to 1.48. Okay, good. We have our equilibrium constant. Wonderful. Well, let's write out an ICE table and see if we can determine what we need to do in order to answer the question. And all we're trying to do is figure out the concentration of everything at equilibrium. So we've got our phosgene in equilibrium with our carbon monoxide and our chlorine. Now this is where reading the problem carefully is really important. So remember, at equilibrium, we have the three concentrations, the phosgene, the carbon monoxide, and the chlorine. But it's saying that those are equilibrium, and that's great. You used that data just to calculate the Kc. But then it's saying, okay, everything's perfectly still, and you throw in an extra 0.1 molar of phosgene, the COCl2. And so that means the initial concentration of the COCl2 is actually equal to 0.0400 molar plus 0.100 molar. So that gives you 0.140 molar. So that tells you when you first start, okay, and of course there's going to be a change here, but you're starting it with 0.140 molar of this and 0.243 molar of each of these. And if you're thinking, Mr. Dion, that's not an equilibrium, that's the point. Okay? No, it's not an equilibrium right now, is it? Okay, but something's going to happen to establish equilibrium. Now, my question for you is this. What's my change going to be? The stoichiometric coefficient of everything is a 1. I got a 1 and a 1 and a 1. Okay, so just x it's either a minus x or a plus x. My question to you is, here, would I put minus x or would I put plus x right there? What would it be for the COCl2? And it's not a trick. Sorry, I can't read what you put, Brogan. It just looks like a dot on the screen.
Is it plus?
No, it would be minus x. Let's think about this with respect to Le Chatelier, our buddy Le Chatelier. Okay, we have reactant over here, and we've got product over here. What did we do? When everything was perfectly at equilibrium, we had 0.400 molar of this. What did we do? We increased the concentration of this, right? We jacked up the concentration of the reactant. So that means that
It's going to make more products.
It's going to have to form more products. Exactly. Now, look, I'm explaining this qualitatively because that's how I would do it on an exam. That's totally what I would do. Another option, there is another way. You could take these three values and you could calculate Q and compare Q to K. You can do that. Okay, but I think it's just a lot more rational to think about it. Okay, well, if I'm adding, I got too much of this, then I'm going to lose some of this, and I'm going to gain some of this, and I'm going to gain some of this, right? So then when I'm at equilibrium, I can just say 0.140 minus x, 0.243 plus x, and 0.243 plus x. Okay? Now, all I have to do is evaluate what x is. Now, x isn't as easy as to determine as it was in some of our other problems. Let me show you why. Because when I use this expression, and that's what I'm going to use right now, I'm going to write it down in red. We know that our Kc is equal to 1.48, which is equal to 0.243 plus x squared, right? Because there's two of these. Why does it do that? Yeah, there we go. Divided by 0.140 minus x. Sorry, I left my squared out. What are we going to have here? We're going to have a polynomial, aren't we? Now, I simplified it to 0.207 minus 1.48x is equal to 0.0590 plus 0.486 x plus x squared. And then I solve for 0, and I get 0 is equal to negative 0.148 plus 1.966 x plus x squared, okay? So again, for that polynomial function, your a in this case is 1, right? It's 1x squared, okay? Your b is equal to 1.966, and your c is equal to negative 0.148. So you would plug all that into your calculator, or you can solve using the quadratic equation. Okay, that totally works. You can use, negative b plus or minus b squared minus 4ac, yeah, divided by 2a. You can do that. You can use whatever you want. But when you solve this, okay, for x, you get that x is going to be equal to 0.0726 molar. Okay, now we're able to figure out all the equilibrium concentrations of everything, aren't we? Okay, it's just a matter of a little bit of addition and subtraction. We do that over here. We get the concentration of COCl2 is going to be equal to 0.140. Subtract this number. I went ahead and did that already. And you get 0.0674 molar. The concentration of carbon monoxide and the concentration of chlorine are going to be the exact same. So it's 0.243 plus this number, and that gives you what? 0.316 molar. There you go. So solving a quadratic. Brogan, to solve this using the Q, all you would do is you say QC is going to be equal to 0.243 squared divided by 0.140. That's all you do. So you take 0.243, you square it, divided by 0.14, and you get that your Q is equal to 0.421. Q is less than KC, okay? And so our reaction is going to have to shift in this direction, right? We're going to have more in the numerator to get a bigger number. That's it. Okay?
So you can't actually find the concentration just doing that though, correct?
No. You got to go the hard way. You got to solve the quadratic in order to figure out this problem. And we'll look at many examples in other chapters too, where we're going to use quadratic equations. So don't think, oh, it's just going to be this chapter. No, you're going to do it in the acids bases chapter. You're going to do it in the equilibria of, other systems chapter. You do it in many chapters in this class. So there you go. All right. Well, let's talk about change in pressure for a second. And since we're getting close to the end of the lecture, I got some good news for you. I'm going to end on a note that is quite digestible, okay? If you're like, my head hurts, Mr. Dion, it hurts, okay? Too much new information. Well, let's end on a lighter topic, and it's the effect on change in pressure. I didn't mean it's an easy topic. What I mean is usually students don't struggle with this concept. Let me show you what it is, okay? It says there's several ways to change the pressure of a reaction, right? If you're in a constant volume system, you've got a couple of options. When you're at constant volume, you can either add or remove one of the gaseous reactants or products, right? Just adding more of it or taking some away. Or you can add an inert gas. This is something you've probably never even thought of in your life. Like, why would I add an inert gas? You guys know what inert means? It just means unreactive, right? Unreactive. Okay, and I'll explain what the effect is. And the other possibility, which I'm sure is more intuitive, would be to change the volume of the container. Okay, but it says here that not all of these lead to a change in equilibrium position. So let's go over it quickly. It says if you're dealing with the first two scenarios, so a constant volume, if you increase or decrease the partial pressure of a single component of the reaction, it's got the same effect as increasing or decreasing that component's concentration. Well, that makes sense because we see how pressure, we see how PV is equal to nRT can be used to solve for pressure, and we see how pressure and concentration are directly proportional to each other. Whereas if we add an inert gas, it changes the total pressure, but it doesn't change anything to do with the concentrations, okay? So the bottom line is with an inert gas, and this will actually be asked on your next exam, and it will probably be asked on your final exam. It's probably one of the easiest questions you'll ever be able to answer because inert gas doesn't do diddly squat. There's your answer. Anytime you see a question about, I added an inert gas to this system of equilibrium, all you have to do is, no change, doesn't change anything, and that's your answer, okay? Just move on to the next question. Now, maybe I don't want to go too fast, but look, here's the bottom line. Let's ignore all this text for now. Let's just look at this beautiful reaction right here, okay? On one side, the reactant side, I have how many moles of gas? I have 4 moles of gases, right? 1 mole of nitrogen and 3 moles of hydrogen. 1 plus 3 is 4. Over here, I have 2 moles of gases, right? Or gas, the ammonia gas. So what's going to be the effect if I decrease the volume of this reaction at equilibrium? Is it going to shift to the left or shift to the right? And the answer is it's going to shift to the side. If I decrease the volume, right, I'm making it smaller, it's going to shift to the side with less moles of gas. Why? Because the more moles of gas you have, the more space they're going to take up, right? You guys remember the ideal gas theory, right? So that's it. And if you're wondering, hey, Mr. Dion, what if I expanded the container? What if I put it in a gigantic container? Then it's going to shift to the left to take up more space. And that's really kind of the last concept I wanted to go over with you today. So you see what's happening down here. You have a certain number of molecules of nitrogen and hydrogen, and then you have some ammonia as well, and you decrease the volume, and look, all of a sudden, now you've got more ammonia molecules in here. Or sorry, no, it's no, there's no change there. Shit. I mean, crap. Anyhow, now you have more ammonia molecules here, and you have less hydrogen and less nitrogen. Anyhow, there you go. And don't worry, I know it's the end of a class. I know you're probably tired. So tell you what, on Monday, what we'll do is we'll start somewhere around here, and yeah, we'll try these. We'll try these problems and pressure and changing, gas. Anyhow, that was a lot of content. We covered a lot of ground, and just by solving a bunch of problems,